Good morning and welcome to the AWS Education Research Seminar Series. I'm Marcy Collinson, your session correspondent and the Scientific Research Programs Manager for the AWS Research Team. Today we are delighted to have Dr. Frank Wuerthwein presenting on GPU cloud bursting for multi-messenger astrophysics with IceCube. Professor Wuerthwein, or Frank as he likes to go by, is an experimental particle physicist at the University of California, San Diego, who analyzes data from the Large Hadron Collider. He is the executive director of the Open Science Grid, responsible for providing an integrated data and compute platform that advances open science through distributed high-throughput computing. Scientists use the platform in the discovery of the Higgs boson, which led to a Nobel Prize in 2013, the detection of gravitational waves leading to a Nobel Prize in 2017, as well as other scientific achievements. We will reserve the last 5 to 10 minutes of the session for a Q&A portion, but please feel free to place any questions that you may have during the presentation in the questions queue in the GoToWebinar toolbar, and we will read them aloud later on. So without further ado, I'll pass the microphone over to Frank. Frank, please take it away.
Good morning, everybody. So as advertised, and you can see here, I'll be talking about a cloud burst on GPUs that we've done last fall, as well as some more recent, a second cloud burst that we have done in February. And I will tell you what was accomplished, how we got there, what the science is, and a little bit about how exactly it was done and cost issues and that sort of thing. Let me start by giving you right away the bottom line. We did this as cloud burst Saturday morning before Supercomputing 19, and on that Saturday we bought all GPU capacity that was for sale worldwide across 3 commercial cloud providers, including AWS. And we then were lucky that we got a hell of a lot of publicity because Jensen Huang picked it up into his keynote at SC19, which was Monday evening. And this is the slide that he talked to for a few minutes. And as you can see on this slide, he advertised us as the largest cloud simulation in history, 50,000 NVIDIA GPUs in the cloud, 350 petaflops for 2 hours, distributed across US, Europe, and Asia. And I'll show you later that we actually misestimated the amount of flops we had, and the actual number in the end after reading our logs more carefully was 380 petaflops at peak. So how did we get here? The annual IceCube GPU use by OSG is shown here on this plot. I've added, I've screen grabbed this plot this morning from our accounting system. And what you see here on the x-axis is time. Every bin is a day, and on the y-axis is GPU hours per day and the different colors are different locations in the world. And so what we do is via a long-term partnership between IceCube, the Open Science Grid, and HG Condor, we support the global operations of IceCube. Basically, they run steady state or not so steady, as you can see in this picture, across a variety of clusters worldwide, peaking at around 3,500 GPUs per day. A lot of this, the vast majority of it, is contributions from IceCube collaborators, and then some of it is just random people who are willing to give their resources, on-prem resources, to IceCube. In the first burst that I will be talking about, we produce about 3% of the annual photon propagation simulations. I'll explain what that means in a 2-hour cloud burst. So 3% of the total annual production in 2 hours. And the pie chart you see here is the pie chart for annual contribution to IceCube by location. And you'll see similar pie charts for the cloud later in the talk, and I'll talk more about that then. So let's switch to the science. I'm going to explain to you what IceCube is and why IceCube needs GPUs. And so IceCube is a cubic kilometer of ice at the South Pole, instrumented with 5,160 optical sensors. So I want to draw your attention to the top diagram here. What you see here is the counting house that you also see an actual picture at the bottom here. And then there is a set of strings that go into the ice. There is about 1.5 kilometers of uninstrumented ice, and then deep down between 1.5 and 2.5 kilometers inside the ice is an instrumentation. And what you should think of, the way this gets deployed is you quote unquote drill into the ice by heating up the ice, turning it into water, and then letting these kind of modules here, a string with these kinds of modules, submerge slowly into the ice so that you have vertical lines up and down with these kinds of digital optical modules spaced apart from each other. And you get a distribution of modules across the kilometer cubed simply by having many strings and many modules per string. This facility is serving a lot of different kinds of science. I mean, I've listed here the science and objectives of the facility, IceCube as a facility, and I will restrict myself in this talk to high energy astrophysics because that's where it connects with multi-messenger astronomy and astrophysics. And one could, in principle, have given talks about all these other things, but this here was the focus of the burst, and I'll explain why. So let's start with a little bit of a primer on high energy astrophysics as it relates to IceCube. On this plot at the top here, you have distance in megaparsecs versus energy in EV. So both of these are on log scales. And what you see here is this black piece. This is the area where the universe is opaque to photons. In other words, if you have, say, a source 10 to the 2 megaparsecs away that throws 10 to the 16 EV photons, meaning something around here, towards us, then they will not reach us. They will disappear, interact in the universe somewhere in the interstellar medium, and voila, we'll never see it. And so the only things that reach us that are far away and high in energy are gravitational waves and neutrinos, and both of them can pinpoint, therefore, the most violent events in the universe. And the name of the game here is to understand the most violent events in the universe, be able to point back at them, and then study them with light that is of which we have lots of in different frequencies. As I'll explain that more in one of the next slides. Fortunately, nature gave us a leg up here in that what you see here is the neutrino energy versus number of events that you expect. You can think of the y-axis as flux of sorts, and the x-axis as energy of the neutrinos. And what you can see here is the blue line is atmospheric neutrinos, meaning neutrinos mostly from the sun interacting with us, our atmosphere, and or actually other particles from space interacting with our atmosphere, producing neutrinos. In fact, it's probably mostly muons producing neutrinos. And then those neutrinos peter out in energy, and the red curve is the astrophysical neutrinos. What this tells you is that astrophysics survives almost background free at high energies. So we have a background free source of astrophysical neutrinos that probe places that light cannot probe, and therefore we have a fundamental addition to our understanding of the universe. Next slide. Here I want to talk a little bit more on what has been actually measured. Here in the previous slide, I talked about the concept. Here I'm talking about the actual measurement. So what you see here is a plot out of a paper published in Science in 2013. This was the first evidence from IceCube that these neutrinos actually exist, and extragalactic neutrinos exist. And on this plot, you can see photons from a satellite, the Fermi satellite, and you can see that as a function of energy here, the photons peter out at around a TeV, and IceCube starts counting neutrinos at an energy of about 10 TeV or so. And so IceCube therefore detects extragalactic neutrinos at very high energies, and these were the first 28 neutrinos observed ever. This proves both that the universe is opaque to photons at high energies and large distances, and it proves that neutrinos exist at these very high energies. Now we get to what do we want to do with this? We want to understand the origin of these highly violent events in the universe, and we have a hypothesis for where they come from. And according to our hypothesis, a cosmic accelerator of sorts, and I'll talk more about this in a second, will throw out both neutrinos and light. If you look at this, and I don't want to go into details, but these two reactions in the end create neutrinos and photons. And so given that these reactions have an energy spectrum, we will detect the highest energy events of this kind via the neutrino, point back in the universe where it came from, and then all the satellites in the world over will try to find it and measure neutrinos at measure photons at lower energy, and therefore we are doing multi-master astrophysics, meaning measuring photons and neutrinos simultaneously. And voila, we understand these most violent events of the universe. That's basically the program. Now, given that neutrinos are very weakly interacting, we need a very large array of ice instrumented. And so, given that we need the help of satellites, we need pointing accuracy so that we can tell them where to look. And so let me talk a little bit about the neutrino detection challenge. And that then brings us to why we do GPU computing, why GPUs are so important to this science. So what you see here in this corner here is the median angular resolution, the median angular error for the pointing accuracy on the y-axis and the deposited energy on the x-axis. And this red curve is the theoretically achievable resolution, and the actual dots is measured events and their resolution. And you can see that it basically is the error is much, much larger than what is theoretically achievable, and the difference is attributed to systematic errors in the instrument. Another way of looking at this is a single event, meaning a single high energy neutrino, and its pointing accuracy back. And what you see these ovals is the measured precision, and the differences of these ovals are different ice models. Depending on what you assume that the ice is actually really looking like in where the detector is, you get very different pointing directions even, not just pointing accuracies. And the reason for this is shown on the right here. The ice properties change with depth and wavelength, and given that we don't construct the ice at the South Pole, nature made it, we have to measure the ice at the South Pole, and we have to simulate it, model it, and figure out what it actually looks like in order to get improvements in pointing accuracy that you can see here from the first set of ice models to possible future improvements given enough GPU power. And that's basically the name of the game, why we use GPUs. GPUs are excellent to simulate photon propagation to ice. And so what is actually being done here is there's a photon program that simulates the shower up to having photons, and then the photons themselves are read into and simulated in the GPUs. So we have an input data set and an output data set, and the output data set is the fully simulated photons. The input data set is the photons from photon simulations to actually see what a neutrino does in the detector. Now, finally, what has accomplished so far on the science? So far, exactly one neutrino has been pointed back. So we have an existence prover, but that's about it. So we have so far seen in 10 years operations of IceCube, one neutrino was found that was pointed back and announced to the world astronomy community. A lot of different satellites and telescopes pointed in real time to that neutrino direction and observed the origin. And there's a gazillion papers published on this. And the primary paper from IceCube and collaborators is pointed to here. You can click on this when you get access to these slides later. And so bottom line, we have a first location of a source, a first indication that the hypothesis may actually be right. And we're now trying to improve the detection capability of the detector and just take more data and collect many of these. Now, where is this going in the future? We want to increase the the IceCube has an upgrade path of about 10 years of constructions and upgrades while they operate the existing detector. And then after 2032, when everything is in place, it expects to run for another 10 years. So the science program I'm talking here about is about 20 years still to go. And it's already running for 10 years. So that gives you sort of the scale of this kind of science. And throughout this time, they will need better and better simulations in order to improve reconstruction and improve pointing back. And so they're improving the detector both for low and high energy neutrinos. And you can sort of see the existing detector is that pinkish thing here. The green detector is one of the upgrades. The extra, there's a high energy array that is more sparse. And then there's a surface array that gets added between now and 2032. That's at least the plan. Now I'm going to switch gears and talk about the burst that we did. The idea is simple. We want to integrate all GPUs available for sale worldwide in a single Condor pool. To do this, we had finances to buy at most 90,000 V100s. And you'll see that number again in a second. And then we just went, well, let's see what we can buy. And we bought, in the first burst, we bought everything that was available. We used 28 regions across AWS, Azure, and Google. And IceCube submitted their photon propagation workflow to this Condor pool. We handle the input, the jobs on the GPUs, and the output as a single globally distributed system. And we run it as a burst relevant in scale for future Exascale HPC systems. In other words, part of this project was to go produce science. Part of it was to show that we can actually burst and show that we can burst that in the cloud to the maximum scale. Part of it was to measure what is the maximum scale available for sale. And part of it was to be prepared for future Exascale HPC systems that we can burst into. Now, how was it done? The global Condor pool is in essence the same technology we use in production for OSG communities in all of science. So there isn't a scientific field that doesn't use this kind of software for something. And we, however, deployed a dedicated hardware setup for just this because we want to avoid disruption of the OSG production infrastructure, and we want to optimize the Condor setup for spiky nature of the demo. Condors normally used for, as the name says, high throughput, but not for high turn on. And so part of this was to deploy something that has high turn on in addition to high throughput. This is what it schematically was deployed. So in each of the cloud regions, we deployed, we brought up VMs that announced themselves to a collector per region. All the regional connectors announced themselves to a global pool, and IceCube as a collaboration, basically one guy in IceCube submitted workflows via schedulers into that one pool, and voila, everything got distributed the world over. The input got pre-staged into native cloud storage because given that the expense is all in buying the GPUs, we did not want to risk in our first attempt anything that could possibly slow us down and could pose additional risks. I'll talk later of in the second cloud burst that we've since actually done bursts that read all the way from home and or are preparing for such a burst. So This is just for the first cloud burst because we're risk averse. We didn't want to have additional risk. Outputs got staged back to the region cloud storage, and then we collected the output after the fact and brought it all back home to Wisconsin. We tested ahead of time that we could sustain the peak of 90,000. This here is the 90,000 peak sustained. This here is the turn on, and you can sort of see that we have up to 60,000 jobs started in 10 minutes. And the colors here are the 28 different cloud regions. We used in this test all the cloud regions that we later on used in production. And the fact that you see here relative sizes is actually our estimate of how many GPUs we might be able to get in each region. This is the actual burst. The actual peak was 51,500 GPUs. We got them, and now here these colors are the actual GPUs we bought in different regions. As you can see, if you compare, it didn't quite work out as planned, meaning there were some regions where we got a lot more than we expected. And the overall, it is very diverse. And now down here, we have a summary of stats at peak. It shows you as a row the number of GPUs and the petaflop 32 for each kind, and each column is a different NVIDIA GPU. We used 8 generations of GPUs all the way from the K520 to the V100s. Basically, we used everything that we could get our hands on. The totality summed up is 380 petaflops at peak of FP32. And let me go through and show you a little bit of, I should probably say that all of these plots have an x-axis of minutes and a y-axis is number of GPUs, basically number of running GPU VMs. Here we slice the same graph up in different kinds of diversities. This here is by GPU type. You can see that we started out with the V100s and the P100s because those are the ones that we assumed would be the most cost effective, and then we started throwing in others and throwing in T4s sort of halfway through with a vengeance. This here is the cloud regions, the 28 cloud regions, and this here dividing up the cloud regions into continents. There is US West, US East, Europe, and Asia. We ran in each one of the commercial vendors, we ran in all of their regions. Therefore, each one of these colors has contributions from each of the 3 vendors. The message here is no one region or GPU type dominates. If you want to really scale to 400 petaflops, you have to basically buy everywhere. The other thing that's interesting is if you look at the events produced per cloud region, it's even more diverse. It's sort of in a sense, it is this plot, but normalized by the power of the GPUs, because it shows the number of signs produced. And what you see here is that no cloud region produced more than about 11% of the total. So if you restricted yourself to just one cloud region, you'd be down by a factor 10. And this also shows the power of the DHCP paradigm, because we can aggregate on-prem anywhere, HPC at any scale, and multiple clouds all into the same resource pool, and therefore maximize globally available resources. I want to talk a little bit about performance and costs, and I will also introduce in the process the second cloud run and talk a little bit about that. The performance is shown in this plot, where I'm showing you 2 pie charts. The pie chart on the left is time spent per GPU type, and the pie chart on the right is events processed per GPU type. And the obvious thing that you see is, while we spend a lot of money and time on K80s, those K80s contributed very little to the total science produced. In contrast, 42% of the science was done on the V100 in 19% of the wall time. We also have plots that are not showing about price per science, basically the amount of science done per dollar for different GPU types. At the time when we did this, the most cost-effective GPU type was the T4 for this kind of science. And we just couldn't buy more of the T4s than what you see here. The second cloud burst focused on maximizing science per dollar. Here we effectively backed off on scale in order to do three things in a way. We wanted to understand how much can we buy of the most cost-effective GPUs, and do so not on a Saturday morning, but on a regular stinking old Tuesday during the day. So we basically burst as an 8-hour workday in Pacific time zone on a random Tuesday in February and wanted to measure what can we do and how much does it cost. Otherwise, we ran the same identical application than previous. And so this here is what you saw. What we saw, we ended up running at about 170 petaflops 32 at the plateau, using only T4s, P40s, and V100s. And we chose those based on our understanding after we analyzed how much could we produce and how much did it cost for each GPU type. And then we picked these three types of GPUs because they were the most cost effective. And then we said, okay, fine, let's see how much can we get. And as you can see, we started with the T4s and first maxed out, bought everything T4s the world had to offer because that was the most cost effective. Then we threw in the P40s and the V100s in order to just get the maximum scale with what money can buy. And in the process of between 9:45 and 17:45, basically on February 4th in PST, we integrated an exaflop hour. So this here shows you the completed jobs, and either which way you slice it, we ended up producing an exaflop hours worth of science, and the total bill was $60,000. You also notice there's a little bit difference between provisioned GPUs and completed jobs. Given that all of this was cheap, we ran this as a spot market effectively. And part of this is preemption, part of this is edge effects when jobs completed and we didn't immediately give back the GPUs. So we kept track of the valuable consumption and, in a way, you can say the waste that we had to pay for. Then the cost to support this. Now, the next question is, of course, how much would this cost if we wanted to offer this as a production capability to anybody in science? So let me talk you through this a little bit. And I'm taking the February 2020 number of cost because the original cloud burst was much more expensive per science dollar, simply because we were focused on what can we get total in scale rather than what do we buy most cost effectively to get the science done. So this is the number that you would do this at if you had to do it again and want to just maximize science per dollar. And so you could buy roughly an exaflop hour for $60,000. And if you wanted to do this sort of thing at scale across many communities, this is the kind of effort that you would have to have in terms of humans. We did this with two people. One guy, Igor Sviligay from SDSC, supported the infrastructure. And one guy at David Schultz at UW-Madison created all the workflows, submitted the workflows, and used the infrastructure. So you can think of David as the science user and Igor the infrastructure provider. And if I wanted to offer this as a financially sustainable service, I would need, in addition, about half an E of a budget manager, because if you do this for many, there's a significant amount of effort required to just deal with costs, budgets, deal with the cloud providers, deal with the customers, and all that kind of jazz. So if I wanted a reasonably modest number, like say a dozen or maybe 24 communities involved at this kind of scale, then I would need about 1.5 FTE. So to provide an aggregate exaflop 32 per day DHC production capability in the commercial cloud for the sum of many, say a couple dozen sciences today would about require 1.5 FTE of human effort and $60,000 of cloud costs per day. This 1.5 FTE of human effort would scale up if you had hundreds of science users, because that half an FTE of budget manager would just go up. The infrastructure support wouldn't go up because we can probably would go up very modestly. I don't think that this is the issue. It's the dealing with budgeting for many users that would blow this up and would be more costly. Moreover, this estimate does not include any human effort to train the community. If you wanted to do something like this as a sustainable effort, you would have to, in addition, have a training effort for the community to teach them how to define workflows, run workflows, and it also doesn't include the scientists themselves that they would have to have funding in order to do this. But at least gives you a sense of what the infrastructure software and infrastructure operations cost would be to do this across the big 3 cloud providers globally everywhere. I wanted to talk a little bit about networking. In fact, I think I'm talking probably way too fast, but we'll deal with this at the end. I wanted to talk a little bit on networking and data. I mentioned earlier that we did design this burst to be mostly compute intensive and only have minimal data and have that data pre-staged such that we have as little pain from moving data around as possible. Now, at the same time, we've actually done experiments in the cloud to see to what extent can we actually loosen up. Because if you wanted to provide this as a service to the community, that sort of is not what people will want to do. A lot of people will want to move data in, move data back out, etc., etc. And so what we've done is we have made measurements of in-region data transfers, between region data transfers, and from region to the outside world data transfers for all areas in the world. And this is published, and there is a preprint on it. It's submitted and accepted as a conference proceeding somewhere. And what you see here is just the throughput reading from object storage in the 3 providers. And you can sort of see that basically they're the same. For all practical purposes, the object storage for the 3 providers is basically performance-wise is more or less identical. I don't consider there to be any difference between these. The difference that you see might be more on our end than in the providers themselves, meaning more the test, the way it was done. And it scales pretty much linearly with number of compute instances. This is basically a number of clients pulling data out of the object storage in a region. Now on this side here, we're showing, can you actually pull data from Wisconsin and therefore not have to pre-stage data in the cloud? And the answer is yes. We've benchmarked this up to about 100 gigabit. Wisconsin has a 100 gigabit connection to Starlight, and at Starlight we peer by Internet 2 with the cloud providers. And so yes, we can put 100 gigabit per second into the cloud all the way to the clients. For this example, we used only one of the regions because we wanted to maximally pull from Madison, Wisconsin into the providers via the Internet 2 peering point at Chicago. And you can see this is the time in seconds, and we started at running clients, and voila, threw them in one after the other, and we peaked at around 10 gigabit per second. That times 8 is 10 gigabyte per second it's 80 gigabit per second, so that's close enough. Peaks reach about 100. Now, so this means that we actually are confident based on our tests that we could do this exercise by reading data from Wisconsin. It just would completely block any and all data transfers. We would basically max out. We would buy as much resource to max out Wisconsin's network connectivity for the entire campus to the research network. The other thing that is worth mentioning is that we measured in these as we did stuff, and also as we brought stuff back from the world, we measured the cost per terabyte of bringing data back home. As everybody knows who has done anything in the cloud, you pay for egress. However, what is probably less known is that there's a very wide spread in the cost for that egress, and I can talk more about the details if somebody wants to know. This egress is of course waived if it stays below 15% of the bill. In other words, if you can afford for free somewhere in the neighborhood of 2 gigabyte per hour on a V100 on the spot market, that kind of production of egress back home is free. Now, to what extent is what we've done applicable to other science customers? Basically anybody that uses the OSG today could do this. We could do this for any of those customers. And those customers include all the large instruments that I know of, LHC, LIGO, DUNE. LSST currently does not use OSG, but what they do is no different. And so we could do that in the cloud. Any mid-scale instruments that I can think of, this includes Xenon in Italy, GlueX at JLab, Class 12 at JLab, NOVA at Fermilab, Dark Energy Survey with its main and archive at NCSA. Any and all cryo-EM basically could be done this way that I know of, because a lot of the main, well, maybe not any and all, there's probably things in cryo-EM that wouldn't, but the dominant cryo-EM reconstruction software these days is a single GPUs or few GPUs, single node capable, and therefore it would be a distributed high throughput computing capable. A large fraction of deep learning, not all of deep learning. There are some deep learning projects that need so much memory that it actually is MPI for the memory consumption and has parallel training. But a lot of deep learning, most of the standard deep learning could be done this way. Basically, one could do anything that has bundles of independently schedulable jobs that can be partitioned to adjust workloads to have half an hour to a few hours of runtime on modern GPUs. As an aside, given that in our first burst, we knew that we were going to use anything from K80s to V100s, we actually prepared different jobs for the low end than the high end. And what we did effectively is the number of photons to be propagated through the ice was different for the low end GPUs than the high end GPUs. Therefore, we curated, so to speak, the jobs to have a reasonable runtime even on the low end GPUs, despite the fact that they are much weaker. Finally, this is my last slide, so I think I'm finishing a bit earlier than I was supposed to. IceCube is ready for Exascale is the main message. And I want to go a little bit, zoom out and talk a little bit about this from a big picture perspective. Humanity has built these extraordinary instruments like IceCube by pooling human and financial resources globally. Experiments like the experiments at Large Hadron Collider, IceCube, LIGO, Virgo, Kagra, those kinds of global scale experiments quite literally pool resources from the world over. The experiment that I do my science with is the CMS experiment at the Large Hadron Collider. My collaboration is about 200 institutions from 45 countries. There is a truly and honestly global effort spanning humanity that is required to make that kind of thing work. Now, given that the effort required, the human effort required to build, design, build, and operate these extraordinary instruments is truly global, the computing of these large corporations fits perfectly to cloud scheduling or exascale HPC systems, because it's by its nature is ingeniously parallel, meaning you can turn this both ways. These collaborations are global, therefore they want to use global infrastructure. The way that we make it affordable to do our science, computing-wise, is by throwing everybody and their brother and sister, provides resources the world over. All of the collaborators, or all the collaborating countries at least, provide some amount of computing resources to the collaboration. That is no different than, that requires the science to work in a way that it is no different than scheduling the entire world's GPU resources in the cloud. So these global efforts are fundamentally globally cloud capable, because by design, their software is designed to be ingeniously parallel. By design, they do things globally distributed. And this paradigm applies to not just these extraordinary instruments humanity has built, but to pretty much, there is places all over that this applies to. It does not apply to everything imaginable. There's plenty of QCD, lattice QCD calculations that you could never do this with, or there is part of molecular dynamics simulations that you could never do this with. So there's plenty of science that cannot make use of globally distributed infrastructure, but there is plenty that can. Finally, we've demonstrated elastic bursts at 51,500 GPUs, and my take-home message is IceCube is ready for the Exascale. And if you want to send me a check and talk about how can we do this for you, send an email either to me personally, to this email address, or to help@opensciencegrid.org. Thank you very much.
Thank you, Frank. That was wonderful. I would like to encourage the audience, if you have any questions for Frank, please don't be shy. Put them in the questions queue. I'd be happy to read them aloud so we can discuss. We do have a few questions. So Frank, the first one I have is, you quote a price range of $20 to $120 per terabyte as egress fees. Why is the spread so large?
So the reason behind this is that given that we're working globally, we get a good price only in the US at the peering points that Internet 2 has negotiated at peering with the cloud providers. The $20 is basically anywhere when we route across those peering points. And the other extreme, the $120, is the worst case scenario when we run somewhere in the world and then have to bring the data home to Wisconsin via the commercial internet. If there were in the future arrangements between global academic providers, for example, GEONT in Europe, if GEONT in Europe had an arrangement with the European cloud providers to get peering and egress charges down to $20 per terabyte, and the routing between GEONT and we were then able to use the routing from, say, I don't know where you guys are actually located, I've forgotten, say Frankfurt. The routing from Frankfurt in AWS goes to GEONT, to Amsterdam, to Manhattan via the known on academic internet, so that we don't charge on the commercial providers. Then we could get this 120 also down to $20. But the spread is literally the routing. Fair enough?
Got it. Yep, that makes sense. So we have a question of, I would like to get a copy of the slides for this excellent presentation. So we will be posting the slide deck along with the recording of this presentation on the past presenters tab of the homepage for the AWS Education Research Seminar Series. So you can look there for those in the near future. Next question. Did you have to coordinate with cloud vendors in advance to buy everything, or did you just offer more in the spot market? Or you just offer more in the spot market?
That's actually a very interesting question, and that gets to this point, the cloud budget manager. Let me present it to you, the answer to you from the cloud provider's perspective, as I understand it. Now, there's a legal principle that you might have rights, but the real rights that you have is only the rights that you can claim, meaning only the rights that you can enforce. Imagine that Jane Doe were to have this kind of access. Jane Doe could run in a day, say, $1 million of charges. By the time that Jane Doe gets her bill, she could have run up charges that she could never afford. Therefore, the cloud providers don't give you just access like this. You have to actually establish a relationship, and via that relationship, you have to be credible that you can pay your bills. And once you're credible that you can pay your bills, they will let you spend as much money as you're good for. And that kind of establishing relationship, that was necessary to pull this off. And so we had meetings with each of the cloud providers. And it actually, to be honest, it wasn't trivial, given that this had never been done before. It wasn't actually trivial to even find the right person in each of the cloud providers that one would talk to in order to get this kind of access. And now that the relationship is established, we can do this any day we want. Meaning they haven't turned us off yet. They still believe that we can pay our bills. And so, therefore, I don't think that this kind of thing is something that is viable to be done by everybody. It makes sense to have it makes sense for the agencies in academia to fund one group, doesn't have to be mine, any one group that can demonstrate that they can do this, and then everybody buys this via that one group, because that way that group establishes credibility with the cloud providers, and that group is then honoring the costs. And therefore, not everybody has to go through what we had to go through in order to be allowed to spend this much money in the cloud. Is that okay as an explanation?
Yeah, I think that's very clear, but if anybody needs a follow-up, please feel free to submit that in the questions queue. The next question is the purchase done as educational or commercial, or a commercial purchase?
That's an even that gets me into the dirty laundry. We actually did both, I believe. We did, given that when we started, we didn't even have accounts with all three cloud providers. We had to be very creative in how we would even pay for it. And one of the most amusing things on the budgeting and paying side was that in order to pay one of the, and I'm not going to tell you which one, in order to pay one of the cloud providers at scale, we actually were granted access to a UK government organization. In fact, the Census Bureau, if I remember correctly, the UK Census Bureau, because they had already established a way of purchasing at large scale. And we used their account for the period of the actual big cloud burst in order to buy from one of the providers. And I can't remember whether we had to do this only in Europe or it was complicated. So short answer is, I think in principle, you could establish these accounts in any which way you want. In practice, given that we did this for the first time, it was a highly non-trivial arrangement, and we did whatever it took. Fair enough?
I think so. Next question is, did you use containers or just plain VMs?
Plain VMs. We're big believers in the KISS principle. keep it simple, stupid. And so we just wanted to, we made containers of, and that already had the software, everything that IceCube needed included, and we made a few such containers in order to start them up in different regions, and so that the container defined where it read data from, and so that we didn't have to do the scheduling of that on top. So we kept things as simple as possible, both in using as much functionality as possible from the cloud side, from the provider side, and as little complexity on our side.
Great. Next question is, you mentioned that what you have done is applicable to many domains of science. If another science project wanted to do this with you, how would that work in practice?
Okay, so in practice, you would send email to one of these two email addresses. We would then figure out whether you want to buy or whether we buy. And in other words, we would have to figure out whose budget is being used. We would offer you our buying capability and offer you to send me a sub-award to UCSD. UCSD does not charge IDC, meaning so that UCSD has overhead-free cloud purchases. That means you could even circumvent your academic institution's IDC charges by sending me money rather than spending it yourself. A lot of universities still charge full IDC, meaning in the neighborhood of 50, 60, 70% on every dollar that you pay for in the cloud. UCSD has 0 on that. And then we would agree on additionally a charge for ego's time, depending on how much you want to do. And voila, we'd agree on when do you want to do it. And off we go. Is that sufficient as an explanation?
It sounds exciting to me. One more question I think we have, and if there are any others, please don't be shy, audience members. Feel free to put them in the questions queue, and we have a few more minutes to try to get to them. What upcoming projects do you have planned?
The upcoming project that is, I've shown you here this view chart. This is actually, for this one, we purchased CPU in the cloud just to benchmark that we can use 100 gigabit from Madison, Wisconsin. We want to make a cloud burst that does not touch any of the storage in the cloud. In other words, we want to pull the data into the cloud and push the output straight back and make it a combined compute and data exercise with as little as possible money spent on storage in the cloud. And that kind of thing we haven't done yet. And the remaining, we have about $100,000 left, I think, in our budget. And that's what we're likely to spend that on. And as you can imagine, to do that sort of thing, you have to be a little bit careful, because you have to effectively control your purchasing of GPU power by knowing how much data it will require to feed and it will produce to store out. And so we're figuring out right now what kind of workflow is the appropriate one to run for this, and how do we do this such that we don't end up spending a lot of money on GPU that produces data that we then can't in real time send back.
Great.
And that's what's left.
Yeah, one more question came through. So can you please summarize the lessons learned and gaps?
The lessons learned, I think a lot of what we learned is, well, there are so many lessons learned. The lessons learned range from what capacity is available, from how do you use that capacity globally, from how much network bandwidth is available inside the cloud providers. To me personally, as somebody who does large-scale data movement around the globe for a living in the LHC community, the fact that the cloud providers have this kind of network capacity available today was an eye-opener. I would argue that it is easier today to move data around inside the cloud than outside the cloud, because we move outside the cloud 100 gigabits. We fill pipes outside the cloud at 100 gigabit, and it's generally a lot of pain and suffering to get there. And inside the cloud, we had terabits. And so that was a big eye opener. Then the complexity of billing was an eye opener. Just like it is incredibly easy to use the cloud, the billing is almost the hardest part. And then another eye opener was let's see. Well, let me think. If you think about what you do in the cloud, nobody ever asked me a single question about security, cybersecurity. I was able to effectively buy let's go back here. I was able to buy a 380 petaflop computer, FP32, in the cloud for a couple of hours, and not ever in any of the conversations with the cloud provider was a single question asked about cybersecurity. Now, if I try to do anything globally in my own field, in academia, with the 100, 200 institutions I work with on a regular day, we had to create cybersecurity mechanism the world over that were incredibly complex and are incredibly complex, with policies, this, that, and the other, and it's just way more complicated. And so I've given a talk a few months ago to a group of cybersecurity experts and CIOs and CISOs at UCSD, a conference of CISOs basically. And I challenged them to think through, why can I do these things in the cloud without anybody asking me a security question? Whereas the first thing that you do when I come to your campus is you ask, let me jump through 3 million hoops to do anything. And I think that's a worthwhile question to ask. I think then there is one small technical thing that you can see that we actually wasted a lot of money in the ramp down. We had actually a bug somewhere between us and the cloud providers, and that sort of is another lesson learned. We basically fixed something, and we didn't have that kind of behavior. If you look at this behavior versus the second time around, we basically dropped like a rock and didn't have any funky overcharges. I think that's pretty much it.
Yeah, no, I think that's great. So I want to thank you so much for the time today, Frank. Very compelling discussion and presentation. We really appreciate you helping us with the series. I wanted to let our audience know that we do have our next session coming up on May 28th at 9 a.m. Pacific Standard Time, and that will be with Dr. Rob Fatland, who is the Research Computing Director at the University of Washington. Dr. Fatland will be discussing a new program called Cloud Bank and research computing on the cloud at the University of Washington. Upcoming session information will soon be available on the AWS Education Research Seminar Series homepage, so please be sure to check that page and register there. We want to thank you all for joining, and have a wonderful day.